Hi, let's look at a trap that beginners can fall into when using SPICE, and in particular the AC analysis tool. So what I've got here, let's say you need to design a circuit. You've got a signal, a 1 volt peak-to-peak signal that you want to amplify, and you want a gain of 10. Got a really simple non-inverting amplifier set up here. We're running it on a bipolar plus minus 15 volt supply. Okay, all looks good. So it's 1 plus RF over Rin, so 9 over 1 plus 1, so gain of 10. Brilliant. So you may think, okay, let's do an AC analysis and get a bode plot and look at the response, the output of the circuit. Okay, so I've set up an AC analysis here, 1000 points per decade, 1 hertz to 10 meg. Okay, so let's run that analysis now. So if we probe the output, there we go, there's our bode plot. So we've got the gain and phase, and it all looks good. Now, say we wanted to, we had a signal bandwidth of 10 kilohertz. Okay, so we look here, and yeah, brilliant. We've got a nice flat line. It's rolling off much higher than 10k. So at 10k, you know, we're looking at 20 dB, which is what you'd expect, gain of 10. Brilliant. So you might think that's great. I've got my circuit there. It's all working. Brilliant. I'll go and design it into a product. Okay, but there's a trap here that you can easily fall into. So if you look on the right hand side of the screen here, I've got exactly the same circuit, but I'm going to perform a transient analysis, so a time domain analysis. I've got 10k sinusoidal wave setup with a 1 volt amplitude. Okay, great. So we know from our AC analysis there, yeah, that should be good. So let's just run it and see what happens. Now look at that, that's interesting. That output is certainly not a sine wave, and it's certainly not got a 10 volt peak to peak output. So why is that? It should be right. We're looking back over here, 10k, we've got 20 dB. It's nice and flat, it works well there. Well, the issue is that the AC analysis is a small signal analysis. So what's going on here? The thing to realise is that when you perform an AC analysis, the first thing the SPICE package will do is find the DC operating point. It will then linearise the circuit, which makes the calculations much easier for the SPICE package to handle. Now, it then performs a small signal analysis around that DC bias point. What this means in reality is that once the model's been linearised, you're not going to see any non-linear effects. Now, some of you will probably be well aware, the reason this circuit here is not performing in the time domain is because of the slew rate of this op-amp. If we were to take that frequency down from 10k to say 1k, there we go, we've got a lovely 10 volt peak to peak sine wave, as you'd expect. That's because the voltage swing at the output here is now within the slew rate limits of the op-amp. Okay, so if we go back to look at our AC analysis here, go back to the properties, you'll see here that we have an AC amplitude of 1 volt setup. Now typically you do that because it's easy. You don't need to do any workings out for your gain there, because you've got an amplitude of 1. What if I change that to, say, 10,000 volts? Let's go for that, 10,000 volts. What do you think is going to happen? Let's have a look. Run the analysis. Oh, look at that, that's strange. It's exactly the same shape bode plot. Now, if we have a look here, that's 100 dB, as we'd expect. Let's just change that there to a linear scale. There you go. We've got 100 kV, so 10 kV times 10. So why is that? This can't be right. Surely the op-amp's going to blow up with a 10 kV input. The SPICE package doesn't care. What you've told it is it's found its DC operating point. It's then performed this small signal analysis around that point. The amplitude doesn't matter. Now it's linear, everything will just scale proportionally, linearly around that point. That's the key thing to remember with this. So this is just one example of where you can fall into this trap, and this is a particularly simple circuit. So really, key thing to take away is there's no substitution for performing a time domain analysis, and really the best thing you can do is to prototype your circuit and test it in real life in the lab.